Hello, stats friends. All right, so we're starting our probability chapter here. This is chapter 5. And this, as long as my plans work out the way I think they're going to work out, this should be the last chapter for our first semester. So that's pretty exciting. Probability is actually one of my favorite topics, so I'm pretty stoked. This section in particular is going to cover randomness, the idea of probability, and then also simulation. So we have some learning targets here, not too many. That's exciting. So let's talk about the idea of probability. So, a random process that generates outcomes that are determined purely by chance. Okay, so I think we've heard all those words together in a definition before. We've talked about this. We've seen this in a lot of other classes as well. So let's get our vocab down. Now, a trial is just one repetition of the process. So when we start doing simulations later, you're going to see things like, so many trials were performed. That's how many times they flipped the coin or rolled the die or whatever they're doing. Now here we have a cute little display of the idea of probability over a large number. So if you were to toss a coin and you were only to toss it 10 times, 10 trials, the proportion of the times it lands on heads is going to fluctuate kind of oddly and maybe not how you would predict. So I think we can all think back to when we were little ones and the coin toss would be like tails, 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 and you're like, oh my gosh, the next one has to be heads because it's just crazy to have that many tails in a row. Well, no, each independent coin toss, they have nothing to do with each other. But the idea next to it is if you were to perform that coin toss over many, many, many trials, so in this case 500 trials, the probability of it landing on heads would approach the what we expect to be the 50% proportion. So half the time it should land on heads and half the time it should land on tails. And if we extended that out to 1,000 trials, you would see that even more close to 0.5. Oh, I jumped the gun. There's all my visuals. There we go. All right, so the probability of any outcome of a chance process is the number between 0 and 1, so remember that. It describes a proportion, so sometimes you'll see it as a decimal and sometimes as a percent, sometimes as a fraction. They're all equivalent to each other. And it describes a proportion of times that the outcome would occur in a very long series of repetitions. So not in the short term, but in the long term, what is the probability of that? So the law of large numbers says that if we observe more and more repetitions of any chance process, the proportion, should approach the actual probability. So in this case, tossing a fair coin should land on heads 50% of the time. And we see that illustrated by the law of large numbers. There's a note. It says some people distinguish between tossing a coin several times to estimate the probability of head, meaning that's the empirical probability, and using a computer applet to simulate this random process. So there you go. It would be fun in class. Maybe we'll try that. Maybe we'll all like toss a coin so many times and put our data together. I think that's probably something we could easily do. So let's talk about the idea of randomness. The idea of probability is that randomness is predictable in the long run. So we're going to kind of keep referring back to the coin toss because that's something we've all seen before in our life. So yes, it is random when you toss a coin, heads, tails, heads, tails. But in the long run, it's predictable. So I could make some claims in the long run. That's the idea. Unfortunately, our intuition about chance behavior tries to tell us that randomness should also be predictable in the short run, and that's just not true. You guys are too young for this, but when your friends, start having families, sometimes they'll be girl, 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 and then everyone's like, oh, it has to be a boy on the next one. It must be. And there's families out there that just girl, 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 or the opposite, boy, 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 boy. It's not likely, but it does happen, and it has nothing to do with whether your first child was a girl or boy. So some people use the phrase law of averages, and that's a misguided belief. Okay, so the law of averages is not really a phrase that we're going to say in our stats class. I'll put it that way. That's a misguided belief because they feel like everything will even out in the short run, and that's not how it works. It's in the long run, your proportion will approach the estimated probability. That's the idea for law of large numbers. So let's check our understanding here. We have Pedro. He drives the same route to work on Monday through Friday. His route includes one traffic light. According to the traffic department, there's a 55% probability that the light will be red when he reaches the light. Interpret. Okay. And then our second question has probabilities a measure of how likely an outcome is to occur. Match one of the probabilities with the following statements and then be prepared to defend your answer. I love that. Be prepared because I'm coming after you. All right. So they want to know the 0, the 0.001, the 0.3, the 0.6, the 0.99, and the 1. So let's talk about Pedro and his traffic problem first. And before I move on, please pause the video and jot down your own thoughts on these questions. All right. So in the interpretation of Pedro's uh, probability is that if you take a very large random sample of his commutes, about 55% of the time, that light will be red. So it's not going to be true if he just looks at, his week's worth of commutes. He's going to have to look at a whole lot of sample, far more than just a week or a month. Maybe he has to look out for the entire year of traveling. And then remember the second question was which one of these matches with 0, 0.001, 0.3, 0.6, 0.99, and 1. Oops, there's a third question too. I didn't see that one yet. So this outcome is impossible. It never can occur. That is probability of 0. This outcome is certain. It will occur every single trial. That is a 100% probability. That's a 1. This outcome is very unlikely, but will occur once in a while. So out of our options here, um, this confuses kids because they're like, wait a minute, which one is it? Well, spoiler alert it. They went with the 0.001. It is very unlikely, but could occur. And then in the very long run, if you do enough trials, like for instance, that's 10 hundredths thousandths. So probability wise, 1 in every 1,000th time it would occur. So if you've done over 1,000 trials, you could anticipate it should occur. That's kind of a weird way to think of it. But all right, what was the other question? This outcome will occur more often than not. So again, that wording's a little strange, because a lot of kids are thinking the 0.99, because it's true, it will occur more often than not with the 0.99. They were trying to have you think about the 0.6 because the proportion value of 0.6 means basically it's going to happen more than half the time. So, majority rule is kind of an idea. All right, the third question. A husband and wife decide to have children until they at least have one child of each sex. So again, they're simplifying this example to just be um, uh, but the binary genders, just because in math and it gets difficult if you start talking about other gender options. The couple has had 7 girls in a row. Wow, that sounds terrible. Sorry, girls. Their doctor assures them that they are much more likely to have a boy. Explain why the doctor is wrong. And we've kind of already talked about this, that every time a baby is born, it's random phenomena as to whether, the chromosomes become XX or XY. And it's unpredictable in the short run. I know 8 kids doesn't it does seem like a large sample probably to you as a teenager, but out of all of the children being born in the world, 8 is not a lot. So that's short one. It's unpredictable, meaning each time they have a child, it's a 50% probability of it being a boy or a girl. And therefore, it doesn't matter that you have a gaggle of girls at home. Your next one could be a girl too. That poor father, he probably just wants a boy. Oh, blue box. That means that's the end of day 1. So the lesson is not very long, you might have noticed, because we're going to do so many fun things and simulations and trials in class. So that's why we're saving a lot of time for that. So I'm moving on to day 2 of this lesson, where we're going to talk about simulation. So simulation is the imitation of chance behavior based on a model that accurately reflects the situation. So the process for a simulation is you describe how to use the chance device to imitate one trial of the simulation, and then you tell what you will record at the end of each trial. You perform many trials. Obviously, you're going to record the data, and then you use the results of your simulation to answer the question of interest. So here is a problem. Hey, we know her. All right. In an attempt to increase sales, a breakfast cereal company decides to offer a NASCAR promotion. Each box of cereal will contain a collectible card featuring one of the following drivers. Joey Logano. Okay, now, first of all, I do not follow NASCAR, and I don't know how old this problem is. So if any of these people are not drivers anymore, I apologize. Joey Logano, and also if I'm saying their name wrong, Kevin Harvick, Chase Elliott, Danica Patrick, or Jimmy Johnson. Now, those of you who are not from Harlem watching this video, the reason I said, hey, we know her, Danica Patrick actually grew up just north of us at frankly, our rival school up in Hononegah. The company claims that each of the 5 cards is equally likely to appear in any box of cereal. A NASCAR fan decides to keep buying boxes of the cereal until she has all 5 driver's cards. That's how they get you. All right, she is surprised when it takes her 23 boxes to get the full set of cards. Does this outcome provide convincing evidence that the 5 cards are not equally likely? To help answer this question, we want to perform a simulation to estimate the probability that it will take 23 or more boxes to get a full set of 5 NASCAR collectible cards. So, we don't want to go out and buy a whole bunch of boxes a whole bunch of times to figure this out. We're going to do a simulation, mostly because we're cheap and it just doesn't make sense. Who wants that much cereal? So first, we're going to describe how to use a random number generator to perform the trial. So what they're saying is assign a number 1 through 5 to each of those drivers, generate a random integer from 1 to 5 to simulate buying a box of cereal and looking at which card is inside. Keep generating numbers until all 5 labels from 1 to 5 appear. Record the number of boxes it takes to get all 5 cards. Now, something important to point out here is we do want to allow repetition here. Okay, so we don't want to do that random number generator no repeat option. We want them to be able to repeat because I could imagine in real life you could buy a box of cereal and then your next box of cereal has that same card in it. I don't know if you guys get stuff in your cereal anymore. I feel like that's an outdated thing. All right, so here's what happened. They went ahead and did it, and they got their data of their 50 trials. What we got here? Explain what the dot at 20 represents. All right, so here's all their trials. 20. There you go. You see them. It says one trial, it took 20 boxes to get all 5 drivers' cards. So they did, wow, they spent a lot of time on this, guys. They did the random number generator until they hit all 5 numbers. They did it 50 times, and this is how many times they had to go through. And remember, the trial represents like buying boxes. So there we go. One time, one trial, took them 20 different purchases before they got all 5 cards. So now that that's our result, because remember, she was at what, 23? We have to kind of take that and interpret what's going on here. So using the results from our simulation, estimate the probability that it will take 23 or more boxes. Well, guys, 23, and I don't have the actual data, but this is 20, I don't know if it's 22 maybe? 23, 24, 20, yeah, that's probably 22. 23 didn't even happen, man. So the probability that it would take 23 boxes is 0 out of 50 in our simulation. So according to our simulation data, there is no chance that you would have to buy 23 boxes or more to get a full set. So because it is so unlikely that it would take 23 or more boxes to get a full set, this provides convincing evidence that those cards are not equally likely to appear in the box of cereal. Like there must be a golden ticket type of card where they know everybody wants that card, so they don't put it in a lot of boxes, so it's less likely to be chosen randomly. So our simulation was showing us what would happen out of pure randomness if everything was fair, fair, fair. And turns out what was happening in real life was not set up that way. All right. A basketball announcer suggests that a certain player is a streaky shooter. That is, the announcer believes that if the player makes a shot, the player is more likely to make the next shot. As evidence, the announcer points to a recent game where the player took 30 shots and had a streak of 10 made shots in a row. Is this convincing evidence of streaky shooting by the player? So we're going to assume that the player makes his shots 50% of the time, and that the results of a shot don't depend on previous results. So first question for you, I think there's another one coming up there. Describe how you would carry out a simulation to estimate the probability that a 50% shooter who takes 30 shots in a game would have a streak of 10 or more. The dot plot displays the results of 50 simulated games in which the player took 30 shots. So I feel like I missed a question. Oh, right here. Describe how you would carry out the simulation. Pause the video. I want you to jot down some thoughts before I show you the answer. All right, so they're saying to carry out the simulation, because this person is a 50% make or miss shooter, they're going to let the number 1 represent making the shot and 2 represent missing the shot. Now, it didn't matter how you assign that as long as you kind of defined it. So we begin by assigning the digits, and then we generate 30 random integers from 1 to 2 using our technology to simulate making 30 shots. And we record whether or not there is a series of at least 10 makes in a row. So we would do, random integer 1, comma 2, comma 10. No, I'm sorry, comma 30. And then we would look at those 30 and see, was there a streak of 10 makes. So 1, 1, 1, 1, 1, 1, 1, 10 of them in a row. We would perform that particular simulation multiple times to get multiple trials, and then we would see what percent of the time that there is a streak of at least 10 among the 30 shots. So here in this dot plot, first they want me to explain what the 2 dots above the 9 indicate. So these guys right here. And then our third question is, what conclusion would you draw about whether this player was streaky? Explain your answer. So I would pause the video and jot down your thoughts before I show the answers. So to answer their first question in this slide about explaining what those 2 dots above the 9 represent, those were the 2 trials that resulted in 9 consecutive makes among the 30 shots. So, and I don't think I explained that really well. I think I was missing the point of this. So there was 1, 2, 3, 4 different trials where the player, quote unquote, the simulation made 2 shots in a row, and that was their longest streak. And then there was this many, however that is, they made 3 in a row, and then there's this many for 4 in a row, and so on and so on and so on. So 2 times did they make 9 in a row by chance. So what conclusion would you draw by that? Well, based on the dot plot, there's actually only 1 trial where they had at least 10 makes in a row. And remember, that was due to sheer randomness. That had nothing to do with the player himself. This is random. So if the player's shot percentage truly is 50%, and the result of a shot truly does not depend on the previous shot, then in 50 trials, we'd expect this player to have a streak of 10 or more only about 2% of the time, so 1 out of 50. So that means, by chance, this was a very unlikely phenomena. And it only happened by chance alone, if that's the case. So if the announcer observed that the player making 10 shots in a row, I think he's justified in saying that he is streaky. Now, it's always interesting when you start incorporating like human behavior into probability because, anyone out there who's an athlete knows there's a lot more to the game than just I'm a machine who makes baskets. There's a mental component to the game, and I think anyone who's played basketball before can claim like, yeah, sometimes we get what they call a streaky. They say, "Oh, they're on fire." Well, there's a huge mental bump, right? You start making shots, your confidence goes, you don't second guess yourself, your muscle memory kicks in. So, we don't often see results that are purely mathematical when humans come into play, especially if it's like athletics. So anybody a Bears fan out there will tell you, sometimes you go into a game and you're like, oh man, totally gonna win because look at all that statistics out there. Las Vegas says we're gonna win, and then you know what, guys, we don't win. Pretty bitter Bears fan over here sometimes. All right, I should be in a better mood. Bears haven't even started yet. Oh, man. Again, if you're not from our area, I'm referring to the Chicago Bears, the football team. All right, so learning targets, I think we hit them. We're going to be doing a lot of simulation. We're going to be designing our own simulations. So that's pretty cool. And that's that. All right, we got a couple more sections left in this chapter, and they should be pretty exciting. Like I said, we're going to do a lot of work in class where we simulate things and do our own experiments. I shouldn't call them experiments. They should be called simulations. Get better, Abruzzo. All right, good luck, everybody.